All right. So what we're going to be talking about today is a part of Theorem 6.27, and where we're trying to prove something about how well thresholded empirical covariances differ from the true covariances. And we're just going to be looking at a very small part of that proof. It's always a little bit confusing, and there's various pieces moving around. So I thought I'd make a little guide to this still very short proof to help better understand it. So the part that we're going to be working on is this section here, which says that given that the difference between the empirical covariance, the maximum, and this is the maximum element-wise, difference, is less than or equal to some quantity lambda n over 2. This is going to imply something about the operator norm of that difference. So this is going to imply that the operator norm of this thresholded covariance difference is less than or equal to 4 times RQ, and we'll say what RQ is in a second, times 1 minus Q. So the whole point here is that we've got our empirical covariance, and as long as its difference, the maximum element-wise difference, is less than this quantity lambda n over 2, we want to say the operator norm of a thresholded difference is bounded in this way. So now what is RQ? So RQ is defined as the maximum over the rows. So we have D rows in this matrix of JL to the Q. So it's actually greater than or equal to this. So it's some number that's greater than or equal to this. So, you know, we can kind of think of maybe if we took so here is our matrix. We can consider taking the Q norm of a row. So that would be this sum sigma JL to the Q to the 1 over Q. So if we take, how would we write that? Let's say if we could call that sigma J Q, then RQ is going to be greater than or equal to the maximum over the rows of JQ to the Q, something like that. So I don't know if that's very helpful to think about it that way, but there it is. And this holds for Q 0 to 1. Okay, so 1 and then all the non-convex ones. Okay, very good. So how are we going to be proving this? The very first step is to go back to an earlier result where we've shown that somewhere that the operator norm can be related to the maximum row sums. So we've shown somewhere, and so for this bit, it doesn't really matter what's inside these operator norms. It's just a property of operator norms. Is less than or equal to the max over rows of the sum. So this is now the column sum of the differences. So this is minus sigma JL. Okay, so that's good. So now the game is going to be, we're going to be interested in this quantity. So we're interested in this max over rows of this column sum, of the differences along the columns. Okay, so we're going to be interested in this quantity. Okay, so the way we're gonna deal with this is we're going to have to kind of bring in the two facts that we know. First, the fact that that the maximum difference, so we're given that the maximum differences are less than lambda n over 2, and we're also given that we're doing this thresholding. We're thresholding. So we're going to kind of split up this sum into two components over subsets of the columns, for which we can apply these facts to get some kind of a bound on this maximum. And then we're going to bring in this RQ quantity to essentially make that bound independent of the rows. In some sense, we're going to be moving this maximum into RQ, because RQ already kind of has this effect of the maximum built into it. Okay, so how are we going to do that? The very first thing we're going to do is we're going to use the fact that this thresholding is happening. So we're going to define a subset that depends on the rows. So we're going to say let Sj be the subset such that, and I believe in the textbook it says what it says in the textbook is actually incorrect. So it should be hat JL is greater than lambda n over 2. Just double checking that. So in a given row, we're going to separate out the subset for which the empirical covariance is greater than lambda n over 2. Okay, so why is that useful? So now it allows us to actually to now separate out the elements of this sum. Okay, so how are we going to do that? So first, let's consider two cases. Let's consider that L doesn't equal to Sj. In that case, that's going to mean that Sjl is less than lambda n over 2, which means that the thresholded, it's going to get thresholded away. So that means the contribution for lambda n of Sjl minus Jl is just going to be equal to Jl. So this is for L not being in Sj. Okay, now when L is in Sj, so when L belongs to Sj, we're going to use a triangle inequality to split this up. So there's going to be potentially some thresholding happening. So we're going to say this is going to be less than or equal to plus right? So that's just a triangle inequality. Now this part we know is going to be less than or equal to lambda n over 2. I forget which one it is, but it's going to be related that way. And because we're thresholding for this component, because we're thresholding at the level of lambda n, the maximum difference here is going to be lambda n. So either it doesn't get thresholded, in which the difference is 0, or it does get thresholded, in which case the maximum difference will be lambda n. So lambda n. And I forget which one it is, but let's just say that. So the total sum here is going to be less than or equal to 3 halves of lambda n. Okay, so that's very good. So now we can kind of go back up here, and now we're going to let me bring out the laser pointer. I don't know where it went. Anyway, we're going to be able to we've now split the sum, and now we can decompose it in terms of these components. So we've got that maximum j of sum of the thresholding thing minus, let's just write it as thresholding. I'm not gonna is going to be equal to the maximum over J of the sum on L doesn't belong to S of L of sum JL plus sum L belongs to S of L of 3 over 2 lambda n. Okay, so now we've still got these two parts. Now the question is how are we going to deal with them? Okay. All right, so we're going to kind of work with this, and the part and what we're going to do from this point on is going to now try to relate these sums to the R of Q. So the R of Q is going to start kind of generalizing out, making these particular sums relating to this kind of general property of the matrix, which is R of Q. So let's work with the first part. So we've got S of L. We're gonna want to kind of turn this into the form of that we can relate to RQ. And do you remember that RQ? RQ was greater than or equal to some kind of a maximum. It was sum JQ to the Q, JL to the Q. Okay, so now if we're going to kind of bring this in, we're going to want, if we're going to have powers of Q and you want less than or equal to, we're going to want to normalize this so that this quantity, so that these quantities are all less than 1. So we will just write this as lambda n over 2 of sum on L does not belong to S of L JL over lambda n over 2. And now this quantity here, I guess we'll just squeeze that. This quantity is less than or equal to 1, so when you raise it to the power of Q, which is between 0 and 1, it's actually going to increase potentially. So this is going to be less than or equal to lambda n over 2 of sigma JL over lambda n over 2 to the Q. And there should be a sum here. Okay, and so now what is this? So this is sum. So let me just write that out again nicely. On sum L does not belong to S of L, sigma JL to the Q over lambda n to the 2 to the Q. Okay, very good. Well, we've got two bits now. So we've got this top bit, which is just this sum of sigma JL to the Q's. So this is going to be less than or equal to RQ. And now we've got lambda n to the Q interacting with this. So that's just lambda n 1 minus Q. And then we've got this additional term, which is going to be times 2 to the Q minus 1. And now again, because Q is less than or equal to 1, this thing is going to be less than or equal to 1 as well. So this means that this whole sum is less than or equal to RQ lambda n to the 1 minus Q. Okay, so that takes care of the indices of L that were not in S of J. So these were the indices that were very small, and it says that they're going to be bounded by RQ multiplied by this this thresholding value. Okay, so now we have to deal with the other guys, and so this was the sum on. Let me change colors here. So now we have to talk about J belonging to S of L. And let me see what happened with those guys. Oh yeah. Okay, so here it just does something very, very simple. So let's just now we're just going to talk to, in this case, well, we just look at R of Q, and we know that this is, by its definition, is greater than or equal to J is equal to 1 to D. So we're actually ignoring the fact that we've subsetted some of the columns to the Q. And then this is going to be greater than or equal to, so because we're looking at just a subset of those. So that's going to be Sj lambda n over 2. And we know that the elements of sigma JL are all less than or equal to lambda n over 2. So this whole thing is just lambda n over 2 to the Q. So then this gives us the fact that the number of elements we have in that set, which could be anything, is going to be less than or equal to RQ times 2 to the Q times lambda n minus Q. So we've related now the size of these sets containing the large covariances to R of Q and our thresholding parameter. And yeah. Okay, so now we've basically got our 2 bits. So now we can just say, well, the sum on J equal to 1 to d of T sigma minus sigma is equal to the sum on J doesn't belong to SL of plus the sum on J that does belong to S of L. This second part is less than or equal to RQ 2 to the Q lambda n minus Q. And the top part is going to be, as we saw, is less than or equal to RQ lambda n to the 1 minus Q. Okay, and oh yeah, and there was kind of a factor of 3 over 2 missing here, so I think that will do it. So that's going to put that over there. And this should be a am I missing a 1 minus Q? Oh yeah, this was actually a factor of 3 over 2 lambda n. So yeah, that's the important thing. So there was a 3 over 2 lambda n over here. So this becomes R over Q 2 to the Q lambda n 1 minus Q times 3 over 2. And then so when we add these up, this is going to be less than or equal to R over Q lambda n 1 minus Q times, what do we have? We've got a 2 over Q times a, let's see, a 3 halves plus plus 1. And then since this thing is going to just be less than or equal to 2, so it's going to be less than or equal to 2 times 3 over half plus 1, this particular component, which is equal to 4, we end up with the overall result that that we were after. So that's how we get this result. So remember the very first bit is, so we're trying to bound this operator norm, and we've been able to relate this in an earlier exercise. We were able to relate it to the maximum row sums, and now we're going to talk about how to bound those maximum row sums while using the information that we have, which is that the difference between the covariance elements and their empirical values are bounded by this lambda parameter, and the fact that we're thresholding. And the way we do that is we divide the columns initially into a set essentially of the small values and the large values, and we just treat those components of that sum separately. Now for the small values that get thresholded away, their components are just the sum of the absolute values of the true covariance matrix, which we relate to R of Q directly. And for the ones that are large, we apply the triangle inequality to, again, relate them to this thresholding parameter. We end up having to know what the number of elements are in a given row that are large, but we end up then being able to relate that to this R of Q, this kind of maximum, Q norm. And in the end, we just combine those, and we finally end up with a result that the norm is bounded above by this Q norm, but scaled by our thresholding parameter. So hopefully that was helpful, and it was kind of a useful guide through these proofs where sometimes I just don't know where the various pieces are coming from. So hopefully that helped you get a better handle on it. Thanks.